Hi, welcome to the Unit 1.5 Nuclear Reactions Notes. So at the top you want to make sure you have 1.5 nuclear reactions and then the page number. And don't forget to add that to your table of contents in the front. Okay, so at the top we have nuclear reactions, that's the title. And first of all, what are nuclear reactions? Nuclear reactions, a nuclear reaction is a reaction resulting in a change in the nucleus, and that can be the number or arrangement of protons and neutrons. And they're very high energy, so a lot of energy is released during a nuclear reaction. You need to pause the videos now to copy these notes, so go ahead and do so. Okay, so now that we've learned what a nuclear reaction is, there are different types, and that's are the main focus of this first part on nuclear reactions, which what are the types of nuclear reactions. So we're going to start with fusion. Fusion means or occurs when two or more nuclei fuse or combine into one larger nucleus. And this is a higher the highest energy between fusion and fission. This has the highest energy, and it occurs in the sun. So here we have an example of a fusion reaction. You have two nuclei, and they're combining together to form one larger nucleus. Now you may be thinking, well, there's also a neutron. That's not a nucleus, so that's okay. But here we have an example of a fusion reaction. Now, one thing before I continue on, I just want to sort of point out a couple of things. In a reaction, what you're starting off with, so we're starting off with two hydrogen-2 nuclei. What you're starting off with is called your reactants. And whatever you make will be your products. So the thing to remember is that reactants react and products are produced. Okay, so just wanted to point that out. All right, so if you need to copy down these notes, you can pause the video now, and then we'll move on. The next reaction type is fission, and that's when one nucleus, I should say, splits apart into two or more nuclei. And this occurs in nuclear reactors. So here's an example of uranium, and it's being split apart into two different nuclei and then also some neutrons. Now, once again, you may be saying, well, wait a second, I see two things here that are coming together. This, again, is not a nucleus. This is a neutron, okay? So both of these are neutrons, and these three things are also neutrons. So I'm just going to point out here, this is not a nucleus. Okay. So let's go ahead and sort of summarize this, and I like to do that with pictures. So what I'm going to do is for fusion, we're going to start with two smaller nuclei, and they're coming together to form a larger nuclei. Okay, so that's the key thing about fusion, two smaller nuclei forming a larger nuclei. Fission is the opposite. You start off with one larger nuclei, and it can split apart into two or more. In this case, it's just two smaller nuclei. And of course, again, these neutrons are not nuclei, they're just neutrons, they're subatomic particles. So they are important in the reaction, but in terms of our definition, they do not impact our definition. Okay, so if you need to pause the video now to take some notes, you can go ahead and do so. All right, the next ones we're going to talk about are decay reactions. And there are actually three types that we're going to look at, but all decay reactions pretty much have the same thing. The only difference is the particle that is made or produced from the decay reaction. So starting out with the definition. A decay reaction occurs when you have one unstable, so the word unstable nuclei, and that's called your parent, breaks down into a more stable daughter nuclei and a particle. So This reaction is spontaneous, meaning that it happens on its own. There's nothing you need to do to cause it to happen. Whereas sometimes in a fission reaction, like the one you see here, the uranium is relatively stable. It's not going to rapidly decay. So to just sort of get that to happen is they bombard it with a neutron. And you saw that in the previous videos. Okay, so let's take a look at the three different types. You have alpha, beta, and gamma, and in parentheses I put the symbols for alpha particles, beta particles, and gamma particles. If you look at an example of an alpha decay, you start off with uranium-238, and it breaks down into thorium and an alpha particle. Okay, an alpha particle is actually just a helium nucleus, a high-energy helium nucleus. In the case of beta decay, you're starting off with one nucleus here, and then it breaks down into xenon. So you have iodine-131 splits into xenon-131 and emits a beta particle. Now, a beta particle is essentially like a high-energy electron. And actually what's happening during beta decay, the electron comes from a neutron, which becomes a proton. So what happens is you have your neutron, and neutron, remember, is neutral, and you can kind of think of a neutron as having both a proton and an electron. And when that splits apart, it forms a proton and an electron. Okay, so that will be your beta particle. So that's what's happening during a beta decay. So the neutron, which is neutral, splits apart into and becomes a proton, and then emits a high energy electron. Finally, we have gamma decay, where we start with something that's very high in energy, and then it decays by its nucleus sort of rearranges and emits a lot of energy in the form of a gamma particle. But as you notice here, in this case, what your parent and daughter are is the same element. You're not changing elements. Where in the other cases, the elements change. Okay, finally, I want to talk about the nucleus being stable. So nucleus is unstable, and we're going to call that radioactive. So it's unstable or radioactive when the ratio of protons to neutrons are not ideal, and you can see that in what's called the band of stability. Or the nucleus is too big, and that occurs when the atomic number is greater than or equal to 84. So atomic number is greater than or equal to 84. So any element on the periodic table, if its atomic number is 84 or higher, it's going to be radioactive. Okay, and so why does this happen? There are two forces in the nucleus, as you saw in the video: nuclear strong force, which holds the nucleus together, and the electrostatic force. So if the nuclear strong force, which holds it together, is weaker than the electrostatic force, then you're going to have an unstable or radioactive nucleus. Okay, so that is it for these notes. If you need more time to copy the information down, I'm going to give you a moment to copy the decay information down, followed by the nuclear stability information. Okay. The last part is on balancing nuclear reactions. So this is actually going to be something you'll cover in the next lesson, but I'm giving you the notes now so that you have them. So these are called nuclear reactions. They're showing you what you're starting off with, and they're showing you what you're making. Now in a nuclear reaction, what you're starting off with, or in any reaction, is called your reactants, and then what you make are called your products. Notice that the reactants and products are separated by an arrow. So you can sort of think of this as if you're cooking, these are your ingredients, and then this is the food that you're going to make in the end. And that's separated by an arrow. Now, in between each reactant and product, they're separated by a plus sign. The final thing I want you to note is that if you have more than one of the same type of reactant and product, you're going to have a coefficient or a large number in front. So in this case, there are 3 neutrons that are produced in this reaction, so a coefficient of 3 is in the front. So it just gives you pretty much the setup. All right, now, balancing nuclear reactions. Nuclear reactions are balanced following the law of conservation of mass or matter, which states that no matter can be created nor destroyed. So you can change matter into something else, but you can't create it or destroy it. Therefore, the total mass and atomic number on both sides of the reaction arrow must be equal. So what do we mean by that? If we look at this first example, we're starting off with 2 hydrogen 2 atoms, and they're producing a helium-3 and a neutron. If we were to add up the mass numbers on the reactant side, so on the left side of the arrow, so here's our arrow on the left side of it, if we were to add up the 2 mass numbers, we would get 2 plus 2 is equal to 4. And if we add the 2 atomic numbers, we get 1 plus 1 is equal to 2. Okay? If this nuclear reaction is balanced, when I do the same thing on the product side, I should get a 4 and a 2. So 3 plus 1 gives me 4, and 2 plus 0 gives me 2. So that tells me that this reaction is balanced. Let's look at a case where it's not balanced. Here we have a reaction where we're starting with 2 hydrogen 2s, and again I add up the mass numbers on the left side of the arrow, so the reactant side. 2 plus 2 is equal to 4, and I do the same on the bottom for the atomic number. 1 plus 1 is equal to 2. Okay? Now if I go to the product side and do the same thing, so what's on the right side of the arrow, 4 plus 1 is, I get 5, and then 2 plus 0, I get 2. Notice how the mass numbers, 4 plus 1 gave me 5. Notice how the mass numbers, 4 and 5, are not the same, so that means it's not balanced. All right, let's look at a final example here. Let's see if this one is balanced. So we have on the left side of the arrow, so the reactant side, what we're starting with, 235 plus 1. When I add up the mass numbers, I get 236. And on the bottom, I get 92 plus 0, I get 92. Now when I do the same thing on this side, I have 90 plus 143. This coefficient of 3 in front tells me I need to multiply the mass number and atomic number by that 3, because I have 3 of them. So I could also just write this out as 3 separate neutrons. That's what that means. So since I have 3 of them, I would do 90 plus 143 plus 1, 2, 3. And if you add that up into your calculator, you get I'm sorry here, there's an error here. Sorry about that. Yep, you get the 235. And then on the bottom, 38 plus 54, you get your 92. Let me just double check that. Sorry, I think this is supposed to be 142. Sorry, there we go. Okay, and so then you get the 235. When you try the same thing on the unbalanced side, at the bottom here, I'm going to take that out. Make that 2. If you were to add up the top numbers, 235 plus 1. Oops, no, this was right. Let me go back to that. Sorry about that. That is 143. And that is 143. There we go. And you get 236 on both sides. So let me do that again. Okay. All right, so on the reactant side, 235 plus 1 for my mass number gave me 236. And for the atomic number on the reactant side, 92 plus 0 gives me 92. Then on the product side, if I add 90 plus 143 plus 3, because remember there's 3 neutrons here. So 90 plus 143 plus 3 for my mass number gives me 236. And for the atomic number, 38 plus 54 gives me 92. So these two are equal. So that looks good. This is balanced. Whereas in this case, if I were to add it up, I get 235 plus 1 on the reactant side gives me 236. And on the product side, 92 plus 0 will give me 92. I want to check to see if I have the same thing on the so this is my reactant side. I want to check to see if I have the same thing on the product side. So 90 plus 143 plus 1, that doesn't give me 236. That gives me 234. So the mass numbers are not equal. And here on the bottom, I still get the same atomic number, 92. So again, this is not balanced because the mass numbers aren't balanced. So remember that both the mass numbers and the atomic numbers must be balanced on both sides. And we've just seen examples where it was just the mass numbers that are different. If your reaction is not balanced, maybe it will be the atomic number that's different. So you want to make sure you get the same number on both sides when you add them up. All right, that is it for this video. If you need to copy this information down, you want to pause the video to do so. And other than that, have a quality day.